sure, yeah, previous sessions must have left with interesting questions. So to keep you awake even after lunch. So never seats look empty. So okay, assuming that, so I would like to invite our next speaker, Professor Neeldhara Mishra is Srimati Amba and Sri V.S. Shastri Chair Associate Professor at Computer Science and Engineering at IIT Gandhinagar. She completed her PhD from Institute for Mathematical Sciences in 2012 in Theoretical Computer Science and was an Inspire Faculty Fellow at the CSA Department of IISc between 2013 and 2015. Her research and interests include the interplay of structural graph theory and graph algorithms, and techniques in parameterized complexity, computational perspective on combinatorial games, voting mechanisms with a special focus on strategic behavior, fair allocations of resources. She's also interested in visualizations and other methods to communicate computational thinking at an elementary level. So yeah, that's it.
All right. Thank you. Thank you for the introduction, and thanks to the organizers for having me as a part of this very exciting summer school. Welcome back to the afternoon session on day one. So the broad plan for this session is to introduce linear programming as sort of a heavy hammer for designing approximation algorithms. So we're going to see a few examples. Let me just do like a quick sanity check. Can you hear me at the back? You guys good? Okay, all right. I think this is working too. Maybe from within the room, a quick show of hands. Those of you who have seen or used linear programs before, can you? Okay, so that's quite a few of you. How many of you have used LP specifically to design approximation algorithms? Okay, cool. So it's a tool that you've seen before. Some of you have already used it for approximation. Hopefully this means that you see a cool new application for a tool that you know and love. I think there are a few people in the room who haven't seen LPs before, so we're going to start off with a quick sort of a recap or an introduction to what the framework is. We might end up being a little speedy about this, just so that we can pack in everything we want to say, but we don't absolutely have to do that, so please feel free to stop me at any point and ask any questions that you might have. Okay. All right, so a linear program is one way of representing certain kinds of optimization problems. We can't, it's not an all-powerful framework that can represent every problem that you care about, but it can represent a whole bunch of them, as we will see. And there are typically two kinds, the maximization LPs and the minimization LPs. It depends on what your optimization objective is. So you're trying to, you're going for something nice, like you're thinking about revenue or opportunities or profits or things like that. You want to maximize these quantities. But if you're thinking in terms of costs or penalties or losses, then these are things that you want to minimize. And sometimes it's sort of a nice duality between the two. So you can usually, there's a nice way of going back and forth and looking at the same problem from two perspectives. So maybe you want to think of it either in terms of maximizing profits or minimizing losses. And although they're typically morally the same thing, we will see that sometimes from an approximation perspective, like which way you look at it can sometimes make a difference. But there are also sort of a formal sense in which there is an equivalence between, or you can come up with an equivalence between a minimization and maximization problem through this concept of duality, which is kind of the second part of what this session is going to be about. So we'll get there when we get there. But here is an example. You might want to maximize the sum of x1, x2, and negative x3. And these things are called decision variables, and this is your objective function. And the linear in the linear program comes from the fact that this is the objective function is a linear combination of these variables. So we're not allowed to have quadratic terms or higher order terms or funny things like square root or sine or cos. You're not allowed to do any of that. It's just a simple linear combination of these variables. And typically we are going to also allow ourselves like these non-negativity constraints that you see here. These are other constraints that you can impose on the decision variables. So this is basically a family of constraints. And the constraints are also are restricted to being linear. So the constraints are also linear combinations of variables. You can throw in as many as you like. And when I give you a system like this, for instance, perhaps you can find, so what you're trying to do here is set values for the variables x1, x2, x3 in such a way that the function x1 plus x2 minus x3 is as large as it can be, okay? And you're also not allowed to pick values of x1, x2, x3 outside these ranges. So what's the solution to this LP? The solution is the max value that you can attain, along with an actual assignment of values to variables. So what should we set x1, x2, and x3 to be? Correct. So it makes sense that since you're subtracting x3, you want it to be, and you're maximizing this function, you want it to be as small as possible. The smallest value that you can legally give x3 is 0, and the other ones you want to max out, so you will max them out at 1 and 2. So this you can solve by inspection, and the optimal value in this case for this particular program is 3. But you could easily construct LPs that are not as quick to solve by inspection. And maybe for some of you, you're able to do it, but I'm not going to be able to look at this and immediately figure out what the optimal value is. You could do a little bit of trial and error. So for example, you could say, well, maybe I want to try out something like this, and then you observe that some constraint is violated when you plug in those specific values. So maybe you tweak them a little bit. So if you're going to start to think about like how do you come up with an algorithm to solve an LP, you might want to think about, well, can I get an arbitrary starting point, and if I satisfy all the constraints, then maybe I get a little more adventurous and see, well, can I tweak this so that I improve my objective value? But if I don't satisfy all my constraints, then I have to tweak them so that I actually at least satisfy all the constraints to begin with. So it takes some thought to come up with an algorithm that can actually solve LP. So this is something that we have mentioned in passing. So we want our functions, both the objective function as well as the constraints, to be linear combinations of the variables. So you're not allowed to do funky things like, just keep it linear. There are other kinds of programs where you'll have to do a little bit more, and you will see examples of such programs a little bit later in the school. The word program in linear programs is a bit of a historical artifact. It turns out, that I think this was a term that came up at a time when a program was just meant to be like, the program, what's the program for the day? It was supposed to be reflecting some sort of a schedule, presumably because they were modeling scheduling problems. But this is not the usage of program in linear programs is not the program that you're thinking of when you're thinking computer programs. So that's it's a bit of a funny thing about the name, but it turns out it stuck. So that's what we're going to continue to use. This is a generic linear program in n variables and m constraints, and maybe you could also imagine writing this as a matrix, so you could potentially pull out all the constants here. So remember that the xi's are the variables, they are the decision variables, and the aij's and the c's and the b's, they are all constants that actually form the LP. Okay, so if you were to write this as a matrix, you could, so this is typically like the constraint matrix. It just pulls out all of these coefficients and you dump it in that matrix, and then you have the vector of variables, you have the vector of like whatever is on the right hand side here. And similarly, this you can think of as the dot product of two vectors, one that has the constants, the ci's, and one that has the variables, the x's. So in some cases it's just more convenient to think of LPs in matrix notation. It's just a more compact way of writing things down. Okay, and there is also something about like the standard form for LP. So you could of course also write down a minimization LP. You could also say that, well, not all these constraints have to necessarily be inequalities, but it turns out that you can tweak these things. Those are still valid LPs, but you can always, if you think about it a little bit, and I think there are probably slides later that show you how to do it. If you have an LP where the inequalities go the other way, or you have minimization instead of maximization, you can tweak things a little bit. Like multiplying everything by -1 and doing a little bit of jugglery like that to make it come out in this form. So without loss of generality, you can imagine that LP basically looks like this. And let's maybe just quickly do one example to get a feel for what are the kind of situations that you can end up with when you're looking at LP, and then we will come to how to use these to actually design algorithms in a bit. So, okay, we are trying to share a piece of cake between Alice, Bob, and Charlie. This is lifted straight from a Western textbook, so the names are what they are, but okay. So, let's say our constraints for cake consumption are as follows. So, so Alice must have at least as much cake as Bob. Bob must have at least twice as much cake as Charlie, but Bob is like maybe diabetic or something, so he cannot have more than half the cake, so that's another constraint. And Charlie is modestly asking for at least 1/10 of the whole cake. Okay. And there is also what they're willing to pay for their share of the what they're willing to pay, let's say, for the whole cake is these values. Okay. And okay, so these are the prices that Alice, Bob, and Charlie value the cake at. Okay, and you as the seller of the cake, you want to maximize your earnings by distributing the cake between Alice, Bob, and Charlie in a way that you don't. You want them as repeat customers, so you don't want to violate any of their constraints. So the question is, what is the maximum amount of money that you can earn while respecting everybody's preferences? Okay. And one way of doing this is probably by some sort of trial and error and messing around, but we can also write this as an LP. And how would we do that? Well, what constraints do we have for this objective function?
xa greater than equal to xb,
Mm.
and xb is greater than or equal to 2xc.
Right. Yes, so basically I think we should be able to translate all of these English sentences into things with the variables. And also, as a cake seller, you only have one cake, so you have to remember that xa, xb, xc, their sum cannot exceed 1, because you only have one cake to distribute. Like if you had 2 cakes to distribute, then the sum couldn't exceed 2 and so on. So, but whatever. In this case, yeah, so this yellow constraint translates to, like some of you have already pointed out, xa is at least xb. The orange constraint translates to xb is at least 2xc. We also have, in absolute terms, xb is at most half, because you cannot give more than half the cake to Bob. And then you have xc is at least 1/10. Yeah. Okay, so also have that we have only one cake. And you could also throw in, you could also throw in these non-negativity constraints, but notice that because it's a maximization program, anybody desiring to maximize this objective will not assign negative quantities here. I think that's something that's you can infer from the rest of the program, but just for good measure, there is no negative cake in this verse, so this constraint represents that you cannot give out negative fractions of cakes to people. Okay. All right. So, okay. I don't know if we just want to do like a little bit of trial and error to figure out where to begin on this one. So. You could start with saying, okay, let's say Charlie, the thing about giving Charlie only 1/10 is like Charlie values the cake the most. So you probably want to give him a little more of the cake, but then that percolates upwards. You cannot give him too much of the cake because the others are going to struggle meeting their constraints. So in particular, let's say we try to give Charlie 1/5, which I guess is double of what he had originally asked for. Then Bob has to get at least 2/5. And Alice has to get at least 2/5 as well, and 2/5 is still less than half, right? So does this satisfy all the constraints that we have in mind? Okay. All right, so this seems okay. Oh, I see. Sorry, the thing is a bit slow. Okay, so this achieves a certain objective. Hopefully, the arithmetic is okay. Some of you who are fast at this sort of thing can double check. But we earn 118 rupees by doing this. And I guess one question you can ask is, Like, can you do better? Is there a different distribution that does better? Do you think about that for a minute? Okay, let's try to, don't know if that's what I have next. Okay, so let's, okay, sorry. Yeah, so, yeah, if you do XP at half, which is like the maximum that we can give to B, then because A needs at least as much as B, we don't have anything left to give C, so then we are in trouble. Okay, so one way to think about this is, yeah, maybe see if you can tweak anything a little bit more or less, and everything seems like there is some, you get the sense that things are kind of tight. But again, I'll leave you to think about this. Like, how do you actually argue that you cannot do better? Because it's sort of this infinite space of possibilities, and you want to kind of logically reason your way out of it and say that, look, any other way of distributing cake will either not be feasible or will give me less mileage anyway, so I'm not interested. Sorry? If you give something more than 1/5 to Charlie, that's one way of increasing the objective, and it won't be feasible because, yeah, I mean the remaining, yeah, I guess, yeah, I don't know if you do like a 1/5 plus epsilon, and this is going to be 2/5 plus 2 epsilon, and it's going to be 2 of those, yes.
I realize that if you do the, like, put the particular bounds into the constraint xa plus xp plus xe less than 1, you actually get that 1 by 5 must be a strict upper bound for xc.
Okay. So what you're saying is if you plug in, but what do you plug in? Oh, I see. You're saying you plug in all of these inequalities here, and then you can derive that, yeah, 1/5, yeah. So it's a good way of, like, you know, this 1/5 here, you could say was a trial and error arbitrary guess, but you can be a little more systematic about it by saying, look, xa plus xb plus xc, I know that xa is at least xb, so I think you can start fleshing out this side of the inequality based on the constraints that you have, and if you simplify it so that it's all in terms of xc, then you see that xc is at most half, at least half. What did you get?
xc is at most 1 by 5.
At most 1 by 5. So you cannot give, yeah, I think that's what was being pointed out earlier. You cannot give anything more than 1.5, sorry, more than 1/5, 1/5. And I was going to say that you can check that by saying that if it's 1/5 plus epsilon, everything else, you know, kind of the domino effect that you have, you're going to be crunched and you're going to violate one of these constraints. But how did you get the 1/5 to begin with? So a much more systematic way of doing that is by plugging in these constraints, combining them, simplifying to see that there's something about this 1/5. And I think you can do less than 1/5 and be feasible, but then you're going to earn less than 118. So that's roughly the intuition for why this somehow is the correct tightrope situation. Of course, not all LPs are like this. Sometimes you do have multiple solutions that give you the same maximizing or minimizing objective. But in this case, I think this ends up being the only way to do it, I think. Okay, so what if we modify the 1/10 to 1/3? So we now suddenly have a much more greedy Charlie. So if Charlie wants at least 1/3, okay, then do you see that we are kind of stuck? Yeah, that's because Bob wants twice as much as Charlie, so they've already consumed the cake between them, leaving poor Alice to like not have anything. So depending on in which sequence you observe these constraints, you now see that there is really no solution. Okay, so this is what's called an infeasible LP, where no matter what values you assign to the variables, you can see that nothing's going to work out. Now we have another modification, which is that we get rid of the constraint that Bob gets at most half the cake. And I think we've also gotten rid of this one here. So you're somehow now running a magic bakery which has an infinite supply of cake, right? So you know upper bound in the sum of the 3 variables, and Bob can also, like, I think he's recovered from his diabetes, so can get as much as he wants. So with just these 3 constraints, what can you say about the LP? Yeah, there is no upper bound, as somebody is pointing out, because whatever you assign to XC, I can make it bigger, assigning something more, because all these inequalities are veering off in one direction only, so there's nothing stopping me, from this infinite cake glitch you generated for ourselves. So there's nothing stopping you from suffering, basically. So, so this is a too much cake situation. This is an unbounded linear program. Okay. So, LPs can be of three types. Ones that you can solve precisely and you have a max or a min objective that you actually achieve. There could be ones that are the constraints are not constraining at all, and the max or the min can run off indefinitely in one direction. So you make it as small or as big as you want. These LPs are called unbounded. And there could be LPs which are over constrained, so the constraints are too constraining and there's actually nothing that satisfies all of them. In which case you might want to say, well, can you find me a solution that satisfies as many constraints as possible? So that's a optimization version of LP, which we will not be getting into. We will just treat these LPs as infeasible. Okay, so typically there are off-the-shelf LP solvers that you can use if you're interested in actually solving LPs in the real world. And these LP solvers will identify these scenarios, and when you are in a situation where you have an optimal solution, it'll actually find that for you, not just the value, but also like an assignment of the values that lead to your maximum or minimum objective. These are just going to be some pictures that I rushed through. So this, again, essentially for at least, okay, when we have two variables, it's kind of nice to visualize what your constraints look like. In principle, you can talk about the geometry of LPs in higher dimensions as well, but it's just not going to be as easy to draw them out, so that's why I'm confining myself to two variables here. So notice that these two constraints basically translate to those regions in the plane, and we are in the upper right quadrant because of the non-negativity constraints, right? So you have the axes are labeled by the variables. So this is the region where both constraints are simultaneously satisfied. So this is called the feasible region of the LP. And typically the objective function is its own line. And you can imagine, this is a static PDF, so you can imagine dragging this line across the feasible region. And you can look at essentially, okay, so so these lines are, so as you drag this line out across the feasible region, right, the line itself is going to take different values, and the value that you care for is like, as you're doing this, you want to keep track of the values and pick the one that is, in this case, the largest, because it's a maximization LP, okay? So the objective function looks like a line cutting through that feasible region, and in this example, this turns out to be the optimal solution. And typically what's going to happen, if you think about the geometry of LPs, is that these constraints are, in general, they're these hyperplanes, and when you look at the intersection of all these hyperplanes, you get something that's called a polytope, and the points that you're looking for, the points you care about that optimize your objective function, are typically corner points in this polytope, because if you're a point that's like sitting inside, you can typically drag it out to a corner point while constantly improving the value of the objective. So that's why they typically end up being corner points. And so the feasible region is some sort of a polytope or a polygon or whatever, and the objective function is a family of lines. In n dimensions, think of these as half spaces, and the intersection is a convex polyhedron, which makes it like a nice structure that you can actually work with. And this, like we said, is a hyperplane that sweeps through this region that you care about. You don't care about being outside the feasible region because those are values you're not allowed to take based on the constraints. So this is an example of an unbounded LP. So you could have the feasible region, like if your constraints are not sufficiently constraining, when you look at a feasible region, it's open-ended on one side, and so you can take your objective function and drag it out indefinitely in that direction. Its value is increasing forever. So that's what an unbounded LP looks like. And you could also have, okay, I don't have this picture somehow, strangely, but you could easily construct examples of LPs where the constraints are very over-constrained. And so when you draw out the feasible region, the intersection is empty. And so you don't have a feasible region at all. That's an infeasible LP. All right, so Um, okay, so we've had algorithms that solve LPs accurately for a while now. Way back in the 40s, we had the simplex, and I think somebody put out a list of the most commonly deployed, the programs that are run the most often. Okay, and it's a nice trivia game to try and guess what are like the top 10 programs that are run the most often in the real world. And it turns out that simplex was like I think in the top half of this top 10 list. It's the reason for this is not very surprising because LPs as a framework can capture a lot of different problems. So if you're solving a problem, there's a pretty good chance that you can frame it as a LP and then slap a LP solver on top of it. That solves your problem. So what's not to love? So LPs are very powerful sort of a language or a framework for describing problems. So that's why if you have a nice algorithm that solves LPs efficiently, chances are it's going to be very widely used. The interesting thing about simplex is that if you analyze it in a theoretical lens, you can come up with these very how do you call it, like annoying examples on which you can force simplex to take a lot of time. So it's worst case exponential, theoretically speaking. But these examples are really very contrived. They're kind of really made up for this specific purpose. So it turns out that the simplex as a method is really popular still because it performs pretty well in practice on most real world LPs. But then there's also a few other methods that have come around. So I think in the 70s we had the ellipsoid method, which is technically efficient. The worst case can be bounded by a polynomial running time. And in the morning, I think we were talking about how polynomial is our holy grail it's our proxy for efficiency. We say if something runs in polynomial time, it's efficient. But you could go deeper into this comment and like, if the polynomial is a really bad polynomial, maybe it's not as efficient as you want it to be in practice, especially if your inputs are very, very large. So it turns out that the ellipsoid method is not as widely deployed in practice because it turns out to be just slower on the benchmarks that you care about. So it's a really nice algorithm or family of algorithms, but just not as practical. And all the modern methodology around solving LPs is a family of algorithms called interior point methods. There's a very long line of work along these lines. So yeah, I think our focus here is not to get into this black box of how LPs are solved, so I won't really be spending a lot of time on this at all. The idea with the simplex is to try and grab a corner point and basically traverse the corners of this polyhedral region and basically stop when you've found the optimal. But then there's a question of, you are only given this constraint matrix, like you're given this, AX at most B and you're given the CX. So from that, how do you even find a corner point? What is the next corner point? How do you do all this stuff? So this is a bunch of details involved here that I'm not going to get into. Right. Okay, so yeah, I mean there are details that are very deliberately omitted, yeah, the ellipsoid and the interior point methods are even more sophisticated in terms of their operations. So very, very delightful literature if you like this kind of family of problems, but a little bit out of scope for now. Okay. Now, an important construct that we will need for the approximation setting is this idea of an integer linear program, which are LPs empowered with this new set of constraints. So now we are upgrading the vocabulary of what we can write. So previously I told you can write AX at most B subject to some objective CX. Yes?
So how do you ensure that the optimal value is reached only in the corner points?
Actually, it may not always be at a corner point, so I lied a little bit there. It's also possible that you can construct an LP where this thing called a face, which is like one of the hyperplanes, and it's possible that you set it up in such a way that that entire face is optimal. So you could have, this will happen if your objective function, remember your objective function was a line, it was a family of lines. So that family of lines happens to be parallel to one of the faces of the constraint, then that entire face can potentially be optimal for you. So it doesn't have to be a corner point, but it will typically not be an interior point. because you can always come out of the interior, and one of the directions of being pulled, you're going to improve your optimization objectives. So it'll probably not be stuck inside, but the optimal can happen at a corner point or at a face, but there will always be some corner point that maximizes or minimizes your objective. Okay, so good point. So let's come back to integer linear programs. So in integer linear programs, you have this upgraded syntax where I allow you to not only say, some linear combination of the variables is at most something, I also allow you to constrain them to be literal integers. Okay, so this is a kind of constraint that you were not allowed to impose before when you were writing LPs. I cannot say something like, my variable x must be either 0 or 1, but nothing in between. Like, those are constraints that you cannot express with just linear combinations of variables. You cannot exclude everything. That's not an integer. So now I give it to you as an explicit superpower. I say you can write this constraint explicitly. And once you can write this constraint explicitly, there's a lot of funky things you can do. So basically, this is the new kind of constraint that you can write. Let's see an example of how you can use this newfound power to express like algorithmic problems we care about. So knapsack is it's a pretty popular problem. If you haven't seen it before, the idea is that you have a knapsack or a backpack or whatever. It has a certain capacity. It can fit in only so many things, and these are all the items that you can potentially buy off of Blinkit or something. And so you want to buy things. Has a certain weight, has a certain value. It's like the value is how valuable it is to you. But you only have so much total space, so you want to maximize the value while being able to fit everything in the knapsack. Okay. So is the problem clear? Okay. All right. So how do we formulate this as an LP? Let's just think about that for a second. Actually, an ILP, because now we're also allowed to use integer constraints. So essentially, the problem that I'm trying to solve is which items do I pick, right? So in particular, for a given item, the question I'm asking is, do I keep this in my knapsack or do I not keep it in my knapsack, okay? So that's a decision that you have to make. So associated with every decision that you have to make, you should think of decision variables, okay? So let me name and conquer. So for every item, let's create a variable which represents this decision for me, okay? And this is why it's really useful to have integer constraints, because now my variable just takes two values. Do I put it in or do I not put it in? Okay. So xi is in the set 0, 1. If xi is 0, that means I'm not picking up this item. If xi is 1, it means I am picking up this item. Okay. So what is my objective function as a combination of these variables?
Maximize the summation of VJ16.
Exactly right. So we want to maximize the summation of xi times vi. So every time we pick up some item I, I'm getting a value of vi from it, and this multiplier will automatically give me the total value. Okay, so these are called indicator variables or decision variables. So we are trying to maximize value, so it's a maximization LP, and this is what we are trying to maximize. Yeah? Is this kind of okay? Yeah? So if anybody comes up with a proposed solution saying pick up items 1, 5, and 7, then this guy will say, okay, x1 is set to 1, x2, x3, x4 is set to 0, x5 is set to 1, x6 is 0, x7 is 1, x8, x9 is 0 if you have 9 items. Okay. So when you plug in those values for the xi's, the only vi's that survive the sum are the ones corresponding to the items that you picked up. So this objective naturally captures the thing that you're trying to maximize. What is the constraint?
Summation wj xj is less than or equal to w and xi belongs to 0.
Xi belongs to 0, 1 is already a constraint that we have put up there. And now we want to take the weighted sum of the xi. So just like we did the value sum, we have the weight sum. So this is the total weight of the things that we put in. And that has to be at most the capacity of the knapsack in which we are packing in these items. Does that make sense? So the same logic, the terms that will survive the left-hand side of this constraint is the sum of the weights of the items that you chose to pick. Okay. So the sum of the weights of the items that you chose to pick should not exceed capital W, that's the capacity of Is this okay? Yeah? Okay. So great. So you're able to model something like that. So I would notice that if you didn't have integrality constraints, then you would have a hard time doing this, right? Because now the indicator variables are in the range 0, 1, which you're allowed to do. What if xi is like 0.5? Should I pick this? Should I not pick this? Like not clear. Yeah, so this is like, yeah, with the LP it's like you're a stock market advisor telling people like random things, whereas with integrality constraints you can be really precise, saying pick these, don't pick those. Okay, cool. Alright, so I guess here with integrality constraints, okay, I think what I want to be doing here is you could have situations where the LP opt and the ILP opt. What do I mean by the LP corresponding to an ILP is basically take the same program but drop all the integrality constraints, or not drop them so much as modify them. So that's, so for example, if you have the set 0, 1, the corresponding LP will say, well, not the set 0, 1, but the range 0, 1. Okay. So in this case, I've said x1, x2 can be integers, like positive integers. And in the relaxed version, I don't care, I can pick anything I want. So in this case, it turns out that the optimal solution for both the programs with and without the integrality constraints are the same. But in this example, it turns out that if I allow x1 and x2 to be anything, I don't constrain them to be integers, then it turns out that the LP opt is different from the ILP opt. So this can happen, but in general, what's the relationship between the ILP opt and the LP opt for the same set of constraints?
LP opt is less than or equal to ILP.
Lesser than equal to.
Lesser than. Okay, so assuming that you have a maximization objective, the ILP opt is the one that's going to be potentially smaller, right? Because whatever you can do with ILP, you can do in LP, because all of those are, so essentially you're restricting the space of solutions when you go from LP to ILP. So the LP opt cannot be, it cannot be better, let's say, right? With the ILP, you cannot do better than you can do in the LP. Okay. So now, depending on whether you're minimizing or maximizing, those inequalities will look a bit different. Let's say you're maximizing, then the LP will always be at least the ILP. If you're minimizing, the LP will be at most the ILP. Okay. The ILP is going to struggle a bit because it's not allowed to go everywhere the LP is allowed to go. It's not as free. Okay. LP has much more freedom. It can wander away into all these kind of nooks and crannies which are not accessible to the ILP. All right, good. So, yeah.
In the previous case, it can be possible that all the corner points will not be integer.
That's right. So the integer point might actually be, the ILP might be an integer point.
Take the lower of that integer. For example, in 8/3,
Right.
it should be.
Or can you float it or something? Yeah, that's a great question. In general, this is not true for the weird reason that if you could do something like that, you could also solve ILPs efficiently, but we don't know that we can. Yeah, so I think the intuition is that if you do something like floating, like if you do some operation, hopefully it takes you inside the feasible region and not outside of it. And because this was LP opt, it's very close to the LP opt, so it's feasible, it's integer, so it should work out. But I think in general, you cannot efficiently derive the ILP opt from the LP opt. You can derive. Yeah. Yeah, so especially in a higher dimensional thing, like it's not like you will have choices, but maybe there's always a way of bringing it inside, but if it's a very tiny region where by the time you float it, you might fall out of the region because it's a very narrow strip or something. So one thing is that you may not have an operation that cleanly brings you inside into an integral thing. You should be able to set up examples of LPs which have a feasible region, but the corresponding ILP doesn't, because the feasible region is very tiny, and it's squished between 4 integer points, even in 2D, right? So then, no matter what operation you perform, you won't get anything. So that's one argument.
So if there is no floating point of an integer, then you can't say anything about in the geometry.
Yeah, in the geometric interpretation, yeah, I mean, what I do know is that the feasible region for the ILP is still like a well-defined. So the feasible region for the ILP is essentially look at the LP wala feasible region, but then just take the points of the integer lattice sitting inside it, and then you have to find one of these that are the best. Yeah. Yeah, but as it turns out, the thing that we will end up exploiting is that these kinds of rounding mechanisms take you not too far from opt, and that is the approximation connection that we want to make. So hold on to that intuition because it will be helpful. It's just that it won't get us to the exact integer opt. We get us somewhere close, and that's what we want to do later. Alright, cool. So this we have already discussed. I should have changed the slides before I started rambling. But anyway, for a maximization thing, as you all have already pointed out, the LP will in general do better. And this ratio is called the integrality gap. Okay. So it sort of captures like how much better the LP can do relative to its corresponding sister ILP. Yeah. The question we will be interested in often is how big can this gap be for specific situations. In general, you can come up with examples where you can artificially make this gap as big as you want. Again, by constructing these very narrow regions which kind of are very bad for the ILP but very good for the LP. So give the LP a lot of scope and make the ILP suffer, you will be able to push this integrality gap as much as you want. Okay. Alright, so okay, so it turns out solving ILPs exactly is NP complete, which should not be surprising because we were able to use ILPs to model knapsack. So it captures a problem like knapsack exactly, which as you know is a hard problem. So in fact, not just any ILPs, even ILPs where the only constraint, like the only additional constraint is that variables can be 0 or 1. Even ILPs which are so special turn out to be hard, and for the same reason, because you're able to model knapsack. And you could also ask, so this is an optimization problem in the default way that it's presented, but you could also ask the decision question, given an ILP, can you come up with an assignment of values to the variables so that the value of the objective functions at least k? And once you look at this decision question, the membership is an NP because you can actually come up with an assignment of values to variables. Okay, if it's not binary, you have to think about it a little bit. Okay, because your values can be like you have to argue that when you want a short certificate, right? So for those of you who are familiar with how NP certificates work, you want an efficient certificate, so you can't have your values. So if you said something like xi and z, right? So I mean, can you actually ensure that your values, the optimal values of the variables, are somehow related to the size of the program, and they're not arbitrarily large? So that's something to think about. But for binary ILPs at least, the membership is clear. And the hardness, like I said, one way to think about the hardness is that it's a special case of, like, knapsack is a special case of ILP. Like using ILP, you're able to model knapsack. So surely if you can solve ILPs in particular, you can solve knapsack, which is a hard problem. So it's one way of convincing yourself that it's hard. It's by generalization of a hard problem. But if you want an explicit, I think that's as good an argument as any, but if you want some practice in setting up ILPs, you can try to model 3SAT in the language of ILPs. This I will skip because I think we have better things to do, but let's say we all believe that ILPs are hard to solve. Okay. And now let's finally see one example of how we can use LPs, ILPs, and the song and dance between them to get another two approximation for vertex cover. So you've already gotten one this morning using matchings, but let's see how we can also get it using LPs. Okay, so you already know what a vertex cover is. Have a graph. It's assumed simple and undirected and so on. And we want a subset of vertices so that every edge is covered. So this one is a vertex cover, I guess. This one Do you have a vertex cover? Yeah, okay. Yeah. I don't have an example of something that's not a vertex cover, but maybe omit one of these and it's not a vertex cover anymore. So you want to know, do you have a vertex cover of size at most k? So typically two ways of presenting these approximations. You can either say you're looking for a vertex cover of size at most k, and here is an algorithm that's guaranteed to output a vertex cover of size at most 2k if a vertex cover of size at most k exists, okay, and it has no obligation otherwise. On the other hand, you could also treat it as a in this case a minimization problem, and say that we'll get you something that's at most 2 times opt. They're basically equivalent ways of talking about things, and we're going to go back and forth between these styles of expressing our ideas. Okay. Alright, vertex cover as an ILP. Can we frame vertex cover as an integer linear program? What are the decision variables? How many are there? And one associated with each vertex. Like for each vertex, do I pick it in my solution or do I not? Okay. So those are the decision variables. In this example, we have 6 of them. And these are decision variables. Think of them as 0, 1 variables again, just like knapsack. What are the constraints?
If you take any two neighboring vertices, the sum of those two variables should be greater than equal to 1.
Exactly right. Yeah, so I don't know if others got that or people might be listening to the recording. So basically our constraint is, by definition, the vertex cover is supposed to cover every edge using vertices. So we have one constraint per edge. Okay. And so essentially, so we are trying to minimize the sum, and our constraints are, for every edge, the sum of the corresponding decision variables must be at least 1, because it's just literally in English what we are saying is, for every edge, pick one of these guys. So one of these decision variables must be triggered to 1. So the only time you fail this constraint is if you fail to pick both of these, but you shouldn't do that. So that's why this constraint makes sense. Okay. Alright, so that's the ILP. And now the way we are going to get an approximation out of this, so we've already seen that ILP is hard. Actually, there's another reason the ILP problem is hard in general, because we can use it to model vertex cover. So if you believe vertex cover is hard, this is a reduction from vertex cover to ILP. Okay. Alright, so we certainly are not going to be solving this ILP directly, but I think the magic we are going to do is look at the corresponding LP, which is we take the set 0, 1 and relax it to the range 0, 1. Now we have a LP object that we know and love. We have LP solvers that can solve this efficiently for us. So let's solve this efficiently. And the problem is that we're going to get some bizarre stuff, right? So our decision variables are now fuzzy decision variables, right? So x7 is, or let's say x1 is 0.7, x2 is 0.3, x3 is 0.4, who knows what, right? So maybe everything is half. That will satisfy all the constraints, right? In particular. So if everything is a half, like what vertex cover are you going to pick from this? Is the question. Okay. So yeah, so in general, let's say you have a solution like this. I haven't checked if it's anything. I haven't checked if it's optimal or if it's feasible. Hopefully it's feasible. But yeah, so if you have a solution, so suppose LP opt gives you numbers like this. Intuitively, what vertex cover will you pick? Yeah, so the ones that are 0.9 suspiciously look like they should be picked. So this is this idea of rounding, right? So round, so anything that's half or above, let's round it up to 1 and pick these guys. And anything that's less than half, we will ignore. Okay. So this is a rounding algorithm. So this is essentially our algorithm. Run the LP, and for every variable that gets in the LP opt a value that's at least half, take the corresponding vertex and choose to pick it. Okay, it's a very natural rounding thing. Now again, just like in the morning, we have to argue two things. One is that whatever we collected is in fact a vertex cover. And the other thing we have to argue is that it has some relationship with opt, it's not an arbitrarily bad vertex cover. Let's try and argue both of these things. So first of all, I have no idea why I have cardinality of S. This is very strange. Is S a vertex cover? S is the set of chosen vertices. Is S a vertex cover? Okay. Seems reasonable. So suppose not, right? So suppose some edge was left out. what does that
When the
mean?
constraint would not satisfy.
Both XU and XV is less than 0.5.
Exactly right. So we do not pick XU or we do not pick, we do not pick XU and we do not pick XV. And the reason we didn't pick either of them was because they were both below our rounding threshold. They were both strictly less than half. If they're both strictly less than half, then LP failed to do its job, right? So you have a buggy solver or something. It's not satisfying all the constraints. So it's not a valid LP solution. So certainly everything that you have picked covers all the edges faithfully. So it's a vertex cover. It's a good start. Now, sorry, behind the slides, but basically what we said. So it is a vertex cover. Now, okay. So now we want to argue that it has some relationship with opt, but it's also very nice and simple. So notice that the size of S is at most twice LP opt. Why is this? Okay, so so what did we do? We took everything. So the sum of all the decision variables in the LP solution is equal to LP opt, right? We took the things that are already half or more and we doubled them, right? Okay, so in the worst case, the addition, and we've actually also dropped some things, but let's even ignore that, right? So things that were already at least half got, basically their values got doubled, right? So essentially what we have, the number of things that we picked is at most twice LP opt. Does that make sense? Sort of? Yeah? Okay. Alright, so, but LP opt we know is at most opt, right? Because we know that LP opt is the one that does better in general, right? There's a minimization problem, so LP opt is at most ILP opt. But ILP opt is exactly min vertex cover because ILP faithfully modeled the vertex cover problem, right? So we're good. So the fact that ILP opt is exactly min VC, that's what gives us the two approximation in this case. Yeah.
If we round off to something more than half, then can we include a bound or?
Yeah, and it's in the problem set. So yeah, so essentially like why is rounding at half the right thing to do? So in the problem set you asked to try and think about what if you round at a threshold that's less than half. The point is that when we said this is definitely a vertex cover, right? If you round, let's say at 1/4, for example, right? Then now all baits are off, right? Because now you cannot say, well, I didn't pick both of you because okay, let's see.
More than half, right?
Sorry, if you round it more than half, you're going to have this problem. Sorry, if you round it more than half, you have this temptation of improving the bound, right? Because you're rounding now fewer things, right? You're picking fewer things by rounding it more than half. So let's say we round it at 3/4. Sorry, if we round it at 3/4, right? Now we can say, okay, so everything that was 3/4 or above, we pick. Now we have to argue that it's still a vertex cover, right? And now if we try to repeat the same argument, like why didn't we pick XU, it was less than 3/4. Why didn't we pick XV, it was less than 3/4. Well, what's the problem, right? So they could have both been halves, they could have both met the inequality, but we still chose to not pick both of them. So if you increase the rounding threshold, you may not have a vertex cover. If you decrease the rounding threshold, you will still have a vertex cover because the argument is even stronger than before, so you'll still have a vertex cover. But what's the problem with decreasing the threshold? It's that you're picking more things, so you're actually shooting yourself in the foot, right? Because like you're making your approximation ratio worse. So half is somehow like the sweet spot. It's just the right in between thing to do. Okay. All right. So okay. So that's all I had about vertex cover and vertex cover approximation. So LP. So we've seen one example of how to use the LP-ILP relationship to get an approximation algorithm. Now we're going to talk a little bit about duality and see how you can use dual LPs to again get another approximation for vertex cover. And then I still want to talk about set covers like a third theme. So are you guys okay with continuing right away, or do you need like a 2-3 minute stretch break or something? Okay, how many want to break? Okay, that's okay. Feel free to take a break. Maybe we will. Okay, so since we have a couple of more things going, we will continue for now and take a break before coming back to set couple. Okay, got that. Like anybody else who wants to just take a quick break, feel free to. Don't think you'll miss out on much. All right. So once again, how many of you have seen the dual of a LP? Okay, you've done dual constructions before. Okay, nice. Have you used dual to design approximation? Okay, not yet. Okay, very good. So we will do that now. Okay, so let's start off by going over how the dual LP is constructed. Okay, it's kind of this. Yeah, I don't know. These are like two sibling LPs. They're very closely related in many ways. And the motivation for this comes from trying to understand, like before solving the program, let's try and think about just getting a feel for where is opt. By getting a feel for where is opt, all I mean is we want to come up with upper and lower bounds on opt. We want to put a range. Okay. So that's what we want to do. Okay. So you want to say something like opt is at least something, opt is at most something, stuff like that. Okay. All right. So in this case, we're looking at a minimization LP. Okay. So okay, if I want to say that opt is at most v, I can do this by actually showing you a solution whose value is v. So if I show you an assignment to all the variables, such that this assignment satisfies all the constraints, and the objective function takes a value v, then I know that opt cannot be bigger than v, because I'd be like, well, you know, I can achieve v, so what is opt doing, right? Opt should compete with this, and maybe v is actually optimal, or opt if anything is smaller. Okay, so v is then an upper bound for opt. So if you can demonstrate a value, then that's how you get an upper bound. And here actually, what I normally do is get people to make proposals and see like how much of a bound can you get. So I don't know, there's some quick values that we can, like quick solutions that we can come up with. So you're again looking at non-negative variables. Okay, what happens if we set like x1 to 0, for example, because that has a big multiplier in the objective. So x1 to 0, then x2 has to be at least 3 or something because of the second constraint. Okay, so x2 is 0 in your solution. X1 is 2, okay. X3 is 4, okay. So x1 is 2, so 10 minus 4 is 6, so that's tight. And x1 is 2 and x3 is 4, you said, so that's 12. Yeah, that's fine. Sure. So what's the value of your objective? You're getting 14 plus 15. 34? Okay. So we have 34. Does anybody want to bid lower than 34? is there some assignment? Okay, so maybe we can think about competing with 34. I think you can get lower, like maybe even quite a bit lower, I don't know. But anyway, so you should be able to get something in the 20s, I think. But you get the idea, right? So different people are going to come up with different solutions. And so if each one of you gave me a number, I'm going to take the smallest of the numbers that I get from all of you, assuming all of you have solved it correctly and you're giving me feasible solutions, okay? So I'm going to take the smallest number that I get, and that's going to be my best upper bound from this room for the min, okay? Still conceivable that maybe nobody has solved it optimally, and opt may be yet lower, but opt cannot be bigger than this number. Okay? Fair? Okay. But the more interesting question in some sense is, how do you say something like this? Like opt has to be at least something for a minimization LP. Here, like, examples will not work, right? So this one said 34. I know that opt is at most 34. I cannot say opt is at least 34. Somebody in a few minutes will give me another solution that beats 34. So that's definitely not an argument for a lower bound. And if you think about, like, why is opt at least something? Why can't I just make it like so? Okay, so if I only look at the bottom constraint and the objective, so the natural thing to do is to set everything to 0. So opt 0 is as good as it gets. But why can't I get 0? Why must opt be something more than 0? It's because of the constraints. Right? The constraints are forcing me to set bigger values to the variables and forcing opt to go up, even though I want to drag it down. Okay, so somehow any argument for a lower bound saying that opt must be at least something has to somehow come from the constraints. Okay, so let's see, for example, if we look at the expression in the objective function, and I look at what I have here. Is this inequality reasonable? Yeah. So 7x1 is at least x1. X2 is at least minus x2, and 5x3 is at least 3x3. Okay. So term-wise, I can say that this objective, the function that I have, the objective function, the first constraint, have that relationship. So now can you give me a lower bound that is more serious than 0? 10. Right? So objective is at least this, and this is supposed to be at least 10 as per my constraints. Okay? So therefore, opt must be at least 10 for sure. And now can we improve this lower bound? Can we say something more?
It will be greater than 16.
Greater than 16?
If you add 1
Because you
to
get those two.
Mm. Okay, right. So far we have 10. Yeah, so in fact I think the slides jump ahead to 26. Can we do this? Yeah. Because 2 copies of x1 and 1, so that's 7. And then minus 2 plus 2 is 0, so this is fine. And 6 minus 1 is 5, so that's fine too. Okay, so I can take 2 copies of the first constraint and 1 of the second constraint. Right? And so our objective is still at least 2 times this plus 1 times this. But this is at least 10 and this is at least 6. So opt is at least 26.
I think 29 would work for a lower bound.
29, can you get
X1
it?
is 2 and X3 is 3.
X1 is 2 and, you mean for an upper bound? Okay, 29, so you can get, okay, so from 34 we've gone down to 29, and so now you see that we're kind of closing in. That's a smaller range now. Right, so when you want to tighten the upper bound as you're doing right now, you just have to come up with better and better assignments of values to the variables that keep driving the value of the objective down for a minimization problem. But to drive up the lower bound, so you want to drive down the upper bound and you want to drive up the lower bound, right? So to drive up the lower bound, you have to find optimal multipliers for your constraints, okay? So that's another optimization problem, which we can also solve using ILP, because why not, right? So I don't know so this was trial and error. I don't know what these multipliers should be, so let's think of them as variables, right? So in general, I want y1 copies of the first constraint and y2 copies of the second constraint. But I can't just pick any y1 and y2 I like, because if I want to make this argument go through, right, that this objective function is at least, because that's where I get my lower bound from, right? I want to say that opt is at least something. So for this at least to be true, and we want term-wise comparisons, what are my constraints? What's the constraint with respect to x1, for example?
y1 plus 5y2.
Exactly, right. y1 plus 5y2 should be at most 7, right? Similarly, minus y1 plus 2y2 should be at most 1, and 3y1 minus y2 should be at most 5. Yeah, does that make sense? Okay, and okay, so what is it that I want? I want a lower bound that's as big as possible. Right? And what's the lower one I'm going to derive? The lower one I'm going to derive is 10y1 plus 6y2. Right? So I want this to be as large as possible. So my objective is to maximize this. Okay? And it's subject to these constraints. That makes sense? Okay. So this thing that we just constructed, motivated by coming up with a lower bound on the value of the objective, is called the dual LP. Okay? And it has some very nice connections with the primal. The default LP you start out with is called the primal. So notice that your objective was flipped, min became max. Okay? Now every constraint was a variable because you were looking for multipliers for each constraint. So in the dual LP, the number of variables is the number of constraints in the primal. And how many constraints did you have? Well, we were looking for these term-wise comparisons, and there are n terms, as many as there are variables. So the number of constraints becomes the number of variables. The number of constraints in the dual is equal to the number of variables in the primal. That is so. Okay. So, right. So with the dual LP, I think in a lot of presentations, I think it's just presented as the final LP that you get, but I find it much more useful as thinking of it in terms of motivating lower bounds. So if you started off with max, a maximization LP, then you want an upper bound on the objective. It's the same kind of story. And I think this is where the dual LP construction comes from. Of course, you can, now that you know how it's done, you can typically look at an LP, eyeball it, and construct the dual without thinking too much about, why you're doing it. But yeah, so, okay, so this is what the primal and the dual looks like. And, okay, so let's say, can we say something of the relationship between the dual optimal and the primal optimal? Primal again is what we start out with. So, okay, so let's not even worry about optimal so much as let's start off with two solutions, right? So x is feasible with respect to primal constraints and y is feasible with respect to dual constraints. Is there one side of this inequality is there one way that we can write an inequality that feels natural? Okay, f of x is at least dy. Maybe going back here. So this is, okay, I forgot what I said. I think f is the minimization that we start off with. So if we chain these inequalities, yeah, what did we set this up for? What's the relationship between f and y? So, okay, so if you have a solution, so remember that the dual objective's optimal value is supposed to give us a lower bound on the primal's objective, right? So the primal, okay, so I think this should be the primal from my point of view. So this is the primal, okay? It's trying to be as small as it can be, and the dual is kind of obstructing and saying, okay, it cannot be smaller than this quantity, right? So if you have any feasible solution to the dual, okay, the optimal is what we are looking for, because we want a strong lower bound. We want a lower bound that's as big as possible. But let's just say you give me some way, like you guys told me take multiplies 2 and 1, right? So that's some solution to the dual. So any solution to the dual, okay, is basically an obstruction to the primal. It's saying that, okay, f cannot be any smaller than this, right? So in some sense, any valid g is saying that, okay, any f cannot be smaller than this, in particular the minimum also cannot be smaller than this, okay? So the relationship should be g is f most f. Does that make sense? Yeah? Okay, so remember that f is trying to push as low as possible and g is saying you cannot go lower than this, okay? So g is saying, so g is saying f has to be, any f has to be at least e, particularly so since we are interested in ops on both sides, we are saying, okay, even the minimum value that f takes has to be larger than, on this side we want the maximum value that g takes, but this is true for any pair, okay? So yeah, so g is, f has to be at least g, this is what we are saying, for a minimization f. So this basically, if you wanted to prove this formally, this basically follows from construction and chaining the inequalities that we did earlier. So this is called the weak duality theorem, and this flips if you have a maximization, if your primal is a max. So I think essentially the same exercise, but inequality space in the other direction. So in the interest of time, I'm going to kind of skip over this, skip over the details of the construction, but I think one thing that I've done here is that I've treated the primal maximization program as the dual that we ended up with. Okay, so you probably recognize this program as being that one. And if you, so if you work through this, you'll realize that once you take the dual, where do you end up? You end up back at where you started with, and depending on your intuition for such things, maybe you're not surprised at all, or maybe you're like pleasantly surprised, I don't know, like, but if you take the dual twice, you come back to where you started, okay? And you can sort of like, if you stare at it long enough, you see that it really pops out by the definition of how we constructed things. So after sufficient reflection, it's not surprising, but maybe the first time it hits you a little bit like, okay, did we end up at where we started? Turns out that we do. So you can end up proving this formally, as in with generic variables instead of these specific examples, but the spirit of the proof is basically the same. So you have this nice thing. Okay, so there is something called the, okay, so again, you can write all this in a little more compactly. And this is what we have shown. Of course, now the primal is a max. And what we want to show is actually again, I will not get into this proof because of where we are right now. But yeah, sorry, let me just back up a second. Essentially, the strong duality theorem assures us that this inequality goes both ways. But because I want to get to examples of algorithms that you can use using algorithms that you can come up with using this theorem, I will skip over the proof of the other direction of this inequality. But again, it's not a fundamentally difficult proof or anything. It's like basically manipulating the inequalities and understanding what's going on. And there are some corner cases. So remember, we said our LPs can be unbounded, they can be infeasible. So there are some corner, like, yeah, if you start off with, like, think about what happens if you start off with an unbounded LP, what does the dual look like? If you start off with an infeasible LP, what does the dual look like? Those are corner cases that have to be accounted for separately. But if the LP is nice and it has an optimum, then the primal and dual ops coincide. So we set it up in a certain way to be that one gives an upper bound to the other, one gives a lower bound to the other, but it turns out the setup is tight and the values are actually equal. This, at least I personally found genuinely surprising a little bit, but the fact is that the objective optimals coincide between primal and dual. So these are two really tightly intertwined LPs, and the theory of duality is really, really very fundamental to how a lot of things work in this sort of domain. So it's worth sitting down with the construction and the proof of the strong duality theorem even. It's just that right now I think I'm going to prioritize doing the applications, and we can look at this proof offline at some point. Alright, so this is also, I think, some I think what I said earlier, that we are without loss of generality going to write down the LP in a certain form, because if it's not in that form, you can kind of tweak it so that it comes down to the standard form, which is what is written there. So this again, we are going to just say it and leave it at that. The manipulations are relatively straightforward, so hopefully you're either convinced or you can come back and look at this whenever you like. Okay. All right, so this is just an example of how you manipulate a shabby looking LP and massage it into the standard form. You can always do this. So, okay, and then we have something about complementary slackness, which again, let's see. Trying to determine if I want to do this now or circle back to it in a bit. Okay, I think this. Okay, so yeah, I think let's circle back to the complementary slackness criteria in a couple of minutes. Let's see if we can kind of motivate it from a different context. Right now this looks very crowded. Sorry about that. Let's come back to, so now, okay, so just to take a breather and recap where we are. We've seen how you take a LP, could be a minimization or a maximization LP. We worked it out from minimization LPs, and we said that from minimization LP, if you want to give like an upper bound on like opt is at most something, you can do it by exhibition. You can say, hey, look, here is a value, it's a feasible solution, and the objective function takes this value, then we know that opt must have been in competition with this value, so it's at most that. But if we want to get a lower bound, and we want to say, well, no matter what opt is, it must be at least something, that has to somehow be driven by the constraints. So we said if you combine the constraints in a clever way, hopefully you can get some meaningful lower bounds in opt. But what's the most meaningful way to combine the constraints? We don't really know, so we set up the multipliers to be variables, and then you combine those variables into what we call the dual LP. So if you solve the dual LP, you naturally get a lower bound on the objective value of the primal LP. Okay, and now it turns out that, well, not only is the dual objective like a lower bound for the primal objective, these objective functions, when they're optimized in both LPs, they actually coincide. Okay, so the inequality that we saw was the weak duality theorem, which I think hopefully you're reasonably convinced that that works out, because that's practically by construction. But the other side of the inequality requires like a little more of an argument, and that's the full duality theorem, and that's the one I said, well, let's skip that and come back to it later. But now what I want to think about a little bit is how do you use the duality of these two LPs to get approximation algorithms, because that's what we are here for. So again, let me at least try and initiate this discussion for vertex cover. After this, we're going to meet set cover, and you can try to apply the same framework to set cover, which is a slightly more general problem, and that would be a nice exercise to go through. Alright, so recall that this is the vertex cover LP. Now I have sneakily generalized vertex cover to weighted vertex cover. I don't think we were doing it this way before. So weighted vertex cover essentially same as vertex cover, except vertices have weights. Okay, so when you pick a vertex, you pay for it in a manner that's proportional to its weight. So we have the same old decision variables. So x2 tells us, do I pick this vertex or not? But previously we were just doing the sum of the decision variables because we cared about how many vertices the vertex cover. But now these vertices have teeth, you have to account for their weights. Okay, So when you pick XU, you pay a price of WU. So that's why these weight multipliers. This is just like in knapsack. Okay? The constraints are the same. The constraints are not affected by the weights. You still want to cover every edge at least once. Now, what does the dual of this LP look like? So now you know the dual construction. Well, some of the routine things like min will become max. Okay, every constraint will become a variable. Every variable will become a constraint. So what are the variables maybe to begin with? We have one variable per edge. Okay, so we have edge variables in the dual. And what kind of constraints are we looking at? We have constraints corresponding to one constraint per column in some sense. Okay, so remember how we set up the dual? We said you take the multipliers across the constraints, and for these multipliers to work as advertised, right? You want to get these bounds, so you have to run through a column. So you have one constraint per variable. So here variables correspond to in the primal they correspond to vertices. So in the dual we are going to have one constraint per vertex, one variable per edge. Okay. So what's the objective? We are trying to maximize the bound that we are hoping to get. So that's the right-hand sides of all these inequalities, right? So what are we maximizing?
Summation of the edge variables.
The sum of the edge variables. Yeah? Okay with that? Okay. So we are trying to maximize the sum of the edge variables, one per constraint. And now what are the constraints? Well, let's fix, we have one constraint per variable. Variables are vertices, so let's fix your favorite vertex in the graph and look at what constraint does it produce. So imagine that this thing was written out in full, so I'm standing on top of the xv column, okay, so in the objective function that manifests as wv xv. Now if I look down at all the constraints that involve xv, what are those constraints? Edges incident to the variable v. Okay, so those are the constraints that you shine a spotlight on. The other ones zero out xv. They don't, like edges that are not incident on the variable v. Those constraints corresponding to those edges don't contain xv, so we don't care about them. So we have to go to all these constraints corresponding to edges incident on the vertex v and collect their coefficients and say that that must be at most wv. But coefficients in these constraints are just one, right? So all we are saying is if you sum ye, okay, which is the multiplier across those constraints, right? So ye times 1 basically, but the sum is over all edges incident to the vertex v. This is at most wv. Okay, clear? Or is this confusing? It's reasonable, right? So yeah, if it's somewhat generally confusing, like maybe take a small graph and write out the full matrix and just see what's happening. It's not like I'm not pulling a fast one. This is the dual. This is what it looks like. Okay, so yeah, so I guess this is like a small example. So if we had a vertex v and these were the 4 edges incident on it, then these are the variables you would pull out and it would be at most w. Okay. Right, so we care about integer solutions because that's what gives us the optimal vertex covers. But what we have on hand is the LPs that we know how to solve. So once again, so previously we did rounding. Now we're going to do some song and dance with respect to the primal dual. Okay. All right, so let's start off with, so now we're going to describe an algorithm. So far this was mostly setup. We said set up the primal LP that captures this relaxed vertex cover thing and it has a dual. Okay. Alright, so let's start off by setting all our variables to 0. So in the primal LP, what's going on? Is this a feasible solution? Is it a good solution in terms of objective? Okay, it's not feasible, but look, you're minimizing something, it has value 0, which is amazing. It's of course also useless because it's not satisfying any of our constraints, like not even most of them, not satisfying anything. So it's really a bad solution for primal. But what's going on in the dual? Is that feasible? Dual is feasible, but dual is also depressing because
It's a
the
maximum.
maximization problem is stuck with this value of 0. So it's very sad. Okay, so it's sad on both sides for different reasons. Okay, on this side the value is amazing, but it's not feasible. On the other hand, there it's feasible, but it's like it's a terrible value. Alright, so we want to improve our situation because it's a really sad place to start. How do we want to improve our solution? We should do it in some slightly systematic, some slightly guided fashion. So what we're going to do is, okay, the more serious complaint in my opinion is from the primal side because here constraints are not satisfied. Okay, so what we're going to do is try and loop over these constraints and try and make them happier one by one, and we stop when all constraints are satisfied. Okay, so we're going to upgrade the values of some variables and we're going to try and do them carefully. So, okay, so this is what we just said about these solutions. Okay, so let's pick a constraint that looks unhappy on the primal side. Okay, in the beginning, take your pick. Every constraint is unhappy. Just pick any of them that you like. All right. Now, this constraint in the dual corresponds to a variable, right? Primal constraint, dual variable. Primal constraint, dual variable. So what we are going to do is actually try and improve the value of this variable until we can't anymore. Okay. All right. So in this case, we're going to do this in integral steps so that it sort of makes sense. So remember, okay. So if we ask ourselves, okay, one violated constraint corresponds to one dual variable. This dual variable participates in how many constraints? Two. Is that clear? So this corresponds to the edge E, right? Now, which are the two constraints that, so we have a constraint corresponding to every variable, which is every vertex, right? So which two constraints does phi E participate in if E is the edge UB? Yeah, the constraint corresponding to, so remember that the constraints on the dual side are picking out for each vertex, like let's take all the edges incident to that vertex, right? This is what was happening. So now if you focus on an edge instead, right? Who are the vertices who are going to pick out this edge? Those are the two vertices that are sitting at the endpoints of this edge. So ye wala bulayega, wo wala bulayega, right? These two vertices will call on this edge, but nobody else will because this edge is none of anybody else's business. Okay? So there's going to be these two constraints that YE participates in, one corresponding to the endpoint U and the other corresponding to the endpoint V. Okay? So these are the two endangered constraints because if we willy-nilly increase the value of YE, these are the ones that are in danger of being violated. So assume we're starting with a solution where all constraints are satisfied. Now I take a variable, and in this case, if I were to decrease its value, nothing happens because these constraints are all upper bounds. Right? Summation of Y is at most WE. Right? But now I'm increasing the value, so I have a risk of hitting this glass ceiling. Right? So I should be careful about how much I increase it. I can only increase it up to when one of these constraints is tight. Okay, so essentially carefully increase, like it's like turning up the gas, but you don't want to cross boiling point, okay? So the moment one of these constraints is violated, stop increasing the value of this variable, lock it in because you cannot increase this anymore in the future, okay? Now you've locked this value in, okay, which means that, well, this objective function has improved, okay, and whichever constraint complained first, that corresponds to a variable, which corresponds to a vertex, go and pick that vertex in your vertex cover. Okay, if both constraints somehow coincidentally complain at the same time, go and pick both, it's okay. Alright, so this is how you change or modify the primal solution and the dual solution in one round of your algorithm. Okay. Now go back to the primal, like if this was like in your first step, if you hit a global vertex, or okay, somehow you hit not a global vertex, but somehow at some point you're going to have picked enough vertices to actually form a vertex cover, no constraint is complaining in the primal. So that means that everybody is satisfied, this is where we stop. Okay? In the primal, no need to set variables to 1 if you don't have to. Remember, it's a minimization problem, so you don't want to set variables to 1 just for fun. You're setting them to 1 because you have to, because constraints have been violated. Okay, so the invariant that we are maintaining is that with every round that we perform of this circus, we have made at least one constraint happier. We have not, any constraint that was satisfied before is still satisfied, so nobody has become unhappier, so there's a net improvement in the number of satisfied constraints. And on the dual side, you have increased the value of the objective. All constraints were satisfied before, they're still satisfied now. We're not violating any constraints. Okay? We're doing whatever we're doing it with a lot of care. Okay? Alright. So when we stop, we do have a vertex cover by definition practically, right? Because we stopped when no constraints were violated. And we are picking things on the way, so that's a vertex cover. Now it remains to be argued that this vertex cover has some semblance with opt, right? So let's try and see if we can make sense of this. So what's our output? Okay, so let's focus on what we output, right? So we output a bunch of vertices. So let me write this down as WU XU. So XU is the solution that we've been evolving. This is an integral solution by design. So this is the value of the weighted vertex cover. It's the quality of the solution that we have output. Notice that we can replace WU with this expression here because every variable we picked corresponded to a tight constraint in the dual side. Okay? And the tight constraint on the right hand side had the weight of the vertex, and the left hand side it had the sum of all the edges incident on that vertex. Okay, okay, so now doing a little bit of a tomfoolery here. So what happens if I drop the XU non-zero? The value, I want to say that the output is at most something, right? So the value does not, like as long as the value does not decrease, I'm allowed to do a manipulation. Does that make sense? Right. On the right hand side, I want to eventually end up with out is at most 2 times opt. Okay? So if this value goes up, I'm okay, right? Because I'm only doing an at most. So I've only added some terms to the sum by dropping this non-zero constraint. Okay. Okay. So now let's look at what's happening here. Swapped the summations and essentially, okay, so do we see this? That this is, instead of saying for every vertex go over, so now we're doing this for all vertices, not just the ones that we have picked, okay? So for every vertex, look at all the edges incident to it. It's the same as saying pick an edge and look at both of its endpoints. Okay? Yeah, this is just the, it's regrouping of terms and commutativity or addition, multiplication, whatever, okay? So in the top sum, we were originally, the outer for loop was over all vertices, and the inner loop is for every vertex, look at all the edges incident on it. So the entire sum is a combination of edge-vertex pairs, where a pair has a vertex and an edge incident on it. But I can also see this, I can regroup this set so that I do edges first and then vertices. So I pick an edge, loop over the edges first, and then I look at both endpoints of that edge and look at the same product. Right? Okay, so I have this. Okay, XU, XP are primal variables. Let's think about. So, sorry, just give me 1 second. All right, so okay, so XU, XP are primal variables that were at most 1 each. That's just by nature, right? So we set every variable to either 0 or 1. Right? So, so essentially, I'm just saying that these are both at most 1. Could have been 0, but both at most 1. So 2 times YE. But from here, do you see how the rest of this follows? Okay, you pull the 2 out. You have summation YE, which is the primal objective. And the primal objective we know is basically, yeah, so you could also say that it's an upper bound on the, summation y is the dual objective and upper bound on the primal objective, which is off. So this is 2 times on. Okay, so I think that's, yeah, so that's the third, at least the third to approximation that you've seen for vertex cover today. The first one was using matching, second one's using LP, ILP, LP rounding. This one's using primal dual. So complementary slackness is something that, okay, we're going to come back to it at some other point, perhaps. Now, this is a walkthrough, so I'll leave you with the slides so you can try to, actually, it's a good idea to run through the algorithm in a small example to get a feel for what's going on. Okay. I think I'm more than out of time, I think. Okay, let me just take 2 minutes to introduce set cover because that's what I was officially supposed to do, and all of this is okay. So I will find a way so for you to take a look at these slides offline. But okay, so there are lots of nice motivating examples for set cover that are real world. So I'm not going to do any of those. So this is a toy example. So let's say you want to buy these things. Okay, you want 1 copy of each. But these are only available in these bundles in the supermarket. So you either take everything or you take nothing from a given bundle. So what combination of bundles should you pick so that you have at least 1 copy of each item? So this is the set cover problem. You want to pay as little as possible but get 1 copy of everything. Okay. So you have a universe of 10 elements. You have a family of sets. Each set is going to cost you something. And you want to pick a smallest collection of subsets so that you have the union gives you the entire universe and it costs you as little as possible. So in this version I don't have costs. At some point I will introduce the idea that each set SI comes with a cost CSI or CI. A nice exercise to convince yourself that set cover generalizes vertex cover. Vertex cover is a special case. You can basically think of the family as, well, actually I don't know if I have this the other way around. So you're trying to cover edges using vertices. So just set up the appropriate mapping so that this works out. So you're trying to cover the edges. The family will have 1 set per vertex, but that set being all the edges covered by that vertex. So if you think about it, you should be able to see this equivalence. So try to come up with an LP for a set cover and try and see if the same kind of randomized rounding that we did for vertex cover will work. So the short spoiler alert is that in general there isn't like a clean threshold that you can come up with. If you have a bound for how frequently the universe elements occur in the sets, there's some frequency bounds, then you can use that frequency to threshold. But without the frequency bounds, there's no natural thresholding that will work for set cover. So instead you do something called randomized rounding, which is so just like you did expected value of your max cut algorithm in the morning, here you do randomized rounding and talk about the expected cost of the solution that you output. And the question is, what's the randomization? What's the probability with which you pick a set? That probability is guided by LP opt. So that's the short story. You solve the LP opt values give you like basically a probability distribution which you can use to sample sets from. And then it turns out that basically, let me just skip to the end to tell you that there are 2 kinds of things that you can worry about. You can say, I want to cover everything and I'm willing to pay whatever price. Or you can say that I don't want to pick too many things. I'm happy if I cover like 90% of the universe. Okay, so there are 2 kinds of things that you can do here. Sorry, it's taking a while. You could also do like a greedy algorithm. I think somebody asked this about vertex cover in the morning. Can you pick the vertex that covers the most edges? So here also you can try to pick the set that covers the most edges. And yeah, roughly this is something that you will end up with if you think about it for some time. So you can either get like the optimal cost, but you don't cover your universe. You only get like some 63% coverage. It's not so nice. You can boost it to pay a little more and get better coverage. And you pay even more and you can get full coverage. Okay? And all of this is based on LP and randomized rounding, but you can also do greedy and get a similar log n kind of a bound. So yeah, apologies for time management and for keeping you longer than I was supposed to. But we'll stop here, and I guess we have problem solving coming up, I guess. But yeah, anyway, I'll see you another time during the school. So thanks for your patience, everybody.